Hey guys, Mr. Gardner here. Today we're going to be talking about square roots and cube roots, how to find them, what they mean, and all that jazz. So our objective today is I can use my understanding of exponents to find square and cube roots with 80% accuracy. So we always want that 80% accuracy piece in there because we want to be trying to get 4 out of 5 on the weekly formative. So far we've been talking about using exponents, and we know that exponents show the powers that we're working with, and that we are doing repeated multiplication. When we're looking at roots, when we're looking at square roots and cube roots, now we're trying to look at a number and find out what number multiplied by itself twice equal that number, or what number multiplied by itself 3 times equal that number. Okay, and so those are what we call square and cube roots. So on the page that you see in front of you, I have put the most common up to 12 for each square and cubes. So you can see that 1 squared is 1, 2 squared is 4, 3 squared is 9, and so on. And so then if we're looking at their roots, then that means the square root of 1 is 1, the square root of 4 is 2, the square root of 9 is 3, and all that stuff. And again, if we're looking at cubics, so if we're looking at cube roots, the cube root of 0 is 0, because 0 times 0 times 0 is 0. If we're looking at 1, it's still 1. Then for 8, it's 2, because 2 times 2 times 2 is 8. And I will say, for the most basic understanding of this kind of stuff, memorization's one of your best techniques. But there are some other techniques to find out these things when we look at them. First thing I want to do is look at some terminology. So if we're talking about square roots, we have this symbol here. And this symbol is called the radical. It's totally radical, dude. So it's a symbol that tells us that we're looking for roots. It's called the radical. And then we're going to have a number inside, which is a weird word. It's called the radicand. Okay, so it's the number we're looking for the root of. And then right here, you're going to have the index. And so the index tells us what power of root we're looking for. Now, it's assumed that when we see it just like this, that the index is 2. We don't write it in there. It's just assumed that that's what it is. But anything past 2, we would write it in. So those are cube roots. These are fourth roots, and so on. But for today, we're just going to be working in square roots and in cube roots. So a couple ways we can think about these. So square roots, the best way to think about square roots is just a square using the side length given. So if we're talking about 2 squared, we're talking about a square with sides of 2 by 2. All right, and so you can look at that like that. 2 by 2, that gives me 4. So that's 2 squared, which equals 4. And we can see 1, 2, 3, 4. All right. Now that's a great way to visualize squares, but it doesn't really help us find square roots. So another thing we can do is we can think back to when we did prime factoring. You can think about making a factor tree. Now with 4, we know that 2 goes into 2, and 2 times 2 makes 4. So because I'm given 2 2's as its factors, then I know the square root of 4 equals 2, because my 2 roots are the same thing. So if a number breaks down to having 2 roots, and the roots that you get at the bottom are both the same, then you know that that's that number's square root. Okay? So let's look at a number that's not going to have a nice, easy square root to look at so we can kind of see this. Let's look at the number 6. If I was going to take the roots of 6, I have 2 and I have 3. These aren't the same, so I can't call this 2 squared or 3 squared. That's not going to work, right? So we know that that square root's going to be a little bit tougher to find. Okay, but when we work with perfect squares, we don't really have that problem. So let's look at another one. Let's look at 9. Again, 9 breaks down to 3 and 3. So then I know that the square root of 9 is equal to 3. And so that's really nice. And again, I can look at a square with 9 tiles in it. And there's a 3 by 3 square. 1, 2, 3, 4, 5, 6, 7, 8, and 9. All right, so again, we can look at other numbers. Let's say we're talking about 16. Okay, if we break down 16, we get 4 and 4. And we can see that those two 4s make 16. So the square root of 16 is 4. Okay, and again, we could look at that by making a square. And again, these should all be the same size. And you would see that I have 16 squares inside of there. Okay, so when you see the radical with a number inside, what it's asking you is to tell it what number makes, when multiplied by itself, makes that number. So for 25, we know it's 5 and 5. Okay. The next thing we want to talk about is cube roots. So cube roots are just numbers that we get by multiplying the same number 3 times. So you can think of like 1 cubed is 1 times 1 times 1, which equals 1. So then we could say that the cube root of 1 equals 1. And again, if you think about a cube with side length of 1, then you get a little cube, right? And that cube has a volume that's equal to 1. So when we're talking about cube roots, we're really talking about like volumes of cubes. Okay, and so you can think about 2. 2 cubed is going to be 2 times 2 times 2. And we know that that's 8. So then we could say that the cube root of 8 equals 2. And again, I'm going to make my handy dandy drawing here. We could see that if we made a cube with side length of 2, that this is what it would look like. In all of its beautiful glory. Right, and again, if we were to count up these blocks, I'd have 1 block here, this block here, 3, 4, 5, 6, and then the 2 in the back corner, 7, and there'd be 1 back there, 8. So we can see that that's 8 little cubes in this 2 by 2 cube. Okay, and so that tells us our cube roots. Again, you can see all the different cube roots right here that we would need to know. But basically, you want to just think about what numbers would break up this kind of number to make the multiplication work repeatedly. So I mean, again, if we were to do like 8 and we were to break it down into roots, we would get 2 and 4, and then we break that up, we get 2 and 2. So we can see that all of our factors are 2. Now we want to kind of look at what's going to happen when we have a fraction inside the radical. And it's really simple. There's not much difference that's going to go on there, except for maybe one little thing. So let's say we have a radical, and let's say in there we have 4 and over 25. Well, what we can do with this is we can make this the square root of 4 over the square root of 25 and treat those things as 2 separate square roots. And so in this case, right, we know if we look at our chart or if we memorized it, that the square root of 4 is 2 and the square root of 25 is 5. So then we know that the square root of 4 over 25 is 2 over 5. And it should make sense to check. We can go 2 over 5 times 2 over 5. Remember, when we multiply, it goes straight across, and we get 4 over 25. And that's what we were looking for here in the original problem. And it's no different if we're doing cubics. Nothing's really going to change there. So let's say we're looking for cube roots of a fraction. So let's say in the radical that we have a radical with the index 3, and let's say we have 8 over 27. So if we think about this again, then really what we have is the cube root of 8 divided by the cube root of 27. So here when we look at that, then we know that the cube root of 8 is 2, right? Because 2 times 2 times 2 make 8. And the cube root of 29 is 3, because 3 times 3 is 9, times 3 is 27. Okay, and again, we can think about this as this would be like to the third power, so 2 thirds times 2 thirds times 2 thirds. And again, we just multiply straight across. 2 times 2 is 4, times 2 is 8. 3 times 3 is 9, times 3 is 27. And again, we get the solution we were looking for in the radical. So that's how we evaluate square and cube roots when we have a fraction on the inside.